Okay, now we're going to have an R session to demonstrate the bootstrap. The bootstrap's one of the really powerful tools we have in modern statistics, invented by our friend Brad Efron, just across the road from us here. And what it does is it lets you get at the sampling distribution of statistics for which it's really hard to develop theoretical versions. So the bootstrap gives us a really easy way of doing statistics when the theory is very hard. And to illustrate it, we'll use the example we used in the book in section 5.2, where we have a particularly nonlinear formula for picking an optimal combination of two investments. Okay, so let's have a look at that. Okay, so remember you had two investments, X and Y, and let's say they had risk, which we'll call variance of X and variance of Y. This is a guy who cannot distinguish uppercase and lowercase letters. And we saw, well, we told you that the optimal formula for getting a minimum risk investment, if you're going to use alpha of X and 1 minus alpha of Y, is given by the formula variance of Y minus covariance of X and Y divided by, there we go, lowercase a again, plus variance of Y minus 2 times covariance of X and Y. Okay, so that's a formula, which of course, if we have data on X and Y, we can just compute those variances and covariances and plug them in and compute our value for alpha. Now that's fine, but then you might say, well, what is the sampling variability of alpha? What's the standard error of alpha? Right? How variable is it going to be? Well, that's a nonlinear formula of X and Y, and we just wouldn't know a priori how to do that. This is a case where the bootstrap really helps out. So we'll write a function for computing that formula. It's a simple formula. Given two vectors X and Y of actual data, we write our function alpha, and inside it we compute variance of X, variance of Y, covariance of X and Y, and then we just write out that formula. Okay, and close parens, which means that the function will return the last line that was evaluated, which is actually our alpha. Okay, and so now we've got a data set portfolio which has X and Y in it, and we can run alpha on the X and Y in that data frame. And when we do it, we see that alpha comes up as 0.5758. Okay, so in order to use the bootstrap function, we need to make a little wrapper that allows the bootstrap to work. And this is this function we'll call alpha.fn. And what it does is it takes a data frame and an index, which indexes rows of the data frame, and then computes your statistic, in this case, our alpha index, for which it wants to compute the variance in this case, the standard error. Now what index does, it's going to be an index into the numbers 1 to n. It'll have values of 1 to n, and there'll be n of them. And there can be repeats, of course, because what the bootstrap does is it does a resample of your training observations, and some observations can be represented more than once and some not at all. And index will say which observations get represented, and if they're repeated, that'll be fine, because that's what the bootstrap does. And so what this function does is, let's just enter the function. Okay, it uses the function with, which is a very handy function. With takes first argument a data frame and then some commands. And what it says is, using the data in the data frame, execute the commands. So in this case, we use with data of index, so that gets the right observations. for this particular bootstrap sample, compute alpha of x and y. And the main value of width is that you can use the named variables x and y that are in the data frame. Okay, very handy. All right, let's see if this works. We'll run our function just once using the original index of the data, portfolio 1 to n, and we see we get the same value as we got before. So that works. And so now we'll run the bootstrap. And since the bootstrap involves random sampling, and if we want to get reproducible results, just for purposes of demonstration, it's good to set the random number seed. So there we set seed 1. And now we run alpha.fn one more time, but we take a random sample instead of giving an index 1 to n. So here we've sampled the numbers 1 to 100, sample of size 100 with replace equals true. This is the kind of thing the bootstrap's going to do over and over. Here we just do it once. Okay, so we get a different value of index. That's like a bootstrap sample of size 1. Well, we'll let the bootstrap do the work for us. And so we call the function boot. We give it the data frame portfolio. We give it our little function alpha.fn, and we tell it to do 1,000 bootstraps. Look how fast that was. It's come back already. If we type boot.out, it gives a little summary of the bootstrap, and it tells us our original statistic was 0.575, the estimate, and it gives us the estimate of bias and standard error. We were interested in the standard error. The bias is negligible. The standard error in this case is 0.08, and that's computed by the bootstrap. And you can also plot the bootstrap. It's nice to see what the distribution looks like, and you get a 2-panel plot. One is a histogram, and it looks like a pretty nice symmetric distribution, maybe Gaussian. And in fact, the second plot is a QQ plot, which plots the ordered values against the ordered statistics of a Gaussian. And if it lines up on a straight line, like it pretty much does here, you may say it looks close to Gaussian, maybe a slightly bigger tail on the right. So there's the bootstrap. Very handy way of getting very good, reliable estimates of standard error for nasty statistics.